You exist because of a rounding error, not a metaphor, not an exaggeration, a literal mathematical leftover from the first moments of creation. Roughly 13.8 billion years ago, the universe was born in a blinding eruption of energy, and in that eruption, nature did something it was supposed to do perfectly. It created matter and antimatter in nearly equal amounts. For every billion particles of antimatter, there should have been exactly 1 billion particles of matter. They should have collided, annihilated, and left behind nothing but light. No stars, no planets, no oceans, no you. But something went wrong. For every billion antimatter particles, there were approximately 1 billion and 1 particles of matter. One extra, one leftover, one survivor out of every billion. That tiny surplus, that unexplained remainder, is everything. Every galaxy, every atom in your body, every grain of sand on every beach is descended from that rounding error. And after more than 60 years of searching, the scientists at CERN still cannot explain where it came from. That is what haunts them. To understand why antimatter haunts the physicists at CERN, you first need to understand what should have happened to you, not what did happen. Not the warm story of stars forging carbon and planets cooling into oceans and single-celled organisms clawing their way toward complexity over billions of years. Forget that story for now. Instead, consider what every equation in physics says should have happened. The answer is brutal. You should not exist. Go back. Not to your childhood, not to the last ice age. Go all the way back, 13.8 billion years, to the first fraction of the first second after the Big Bang. The universe at this moment is nothing you would recognize. There are no atoms, no molecules, no light as you understand it. There is no space as you experience it. What exists is an inferno of raw energy so dense, so impossibly hot, that matter itself cannot hold its shape. The temperature is measured in trillions of degrees, and the entire observable universe, every galaxy, every star, every speck of dust that will ever exist, is compressed into a region smaller than the nucleus of an atom. In this furnace, something extraordinary is happening. Energy is converting into matter. This is not science fiction. This is not speculation. This is one of the most rigorously tested consequences of Albert Einstein's equation, E equals mc squared. That equation tells you that energy and mass are two denominations of the same currency. They are interchangeable. When you concentrate enough energy into a small enough space, that energy can crystallize, solidify, congeal into particles of matter. But there is a rule, and the rule is absolute. It is not a guideline, it is not a suggestion. It is a conservation law as rigid as the law that says you cannot create or destroy energy. The rule is this: whenever energy creates a particle of matter, it must simultaneously create a particle of antimatter, always, without exception. If a quark appears, an antiquark must appear beside it. If an electron is born, a positron, its antimatter twin, is born at the same instant. They come into existence as a pair, minted together like two faces of the same coin. This means that in the first microseconds after the Big Bang, the universe was creating matter and antimatter in exactly equal amounts, perfectly balanced, perfectly symmetric. Billions upon billions upon billions of particles and antiparticles popping into existence from the energy field in lockstep pairs. And now comes the part that should keep you awake tonight. When a particle of matter meets its corresponding antiparticle, they do not coexist. They do not bump into each other and bounce away. They do not ignore each other. They annihilate. They destroy each other utterly and completely, converting their combined mass back into pure energy, back into photons, back into light. This annihilation is not some gentle fading. It is the most energetically violent reaction in the known universe. Gram for gram, matter-antimatter annihilation is roughly 200 times more powerful than nuclear fusion, the reaction that powers the sun. A single kilogram of matter meeting, a single kilogram of antimatter, would release an explosion equivalent to approximately 43 megatons of TNT. To put that in perspective, that is close to the yield of the Tsar Bomba, the most powerful nuclear weapon ever detonated in human history. And it would come from 2 kilograms of material, 2 bags of sugar. That is the ferocity of annihilation. So picture the early universe. You have this screaming, roiling ocean of particles and antiparticles being born from energy in perfect pairs. And the instant they are born, they collide and annihilate, turning back into energy. That energy then produces new pairs. Those pairs annihilate. The cycle repeats. Creation and destruction. Destruction and creation. Billions of times per second, in a feedback loop so furious it defies comprehension. The temperature is so staggeringly high that this cycle runs continuously without pause. The universe is a furnace that builds and burns in the same breath. It is assembling and disassembling itself faster than you can blink. And now, ask the question. The question that should terrify you. If every particle of matter was born with a partner antiparticle, and if every encounter between them ends in mutual annihilation, then when the universe finally cooled down enough for this cycle to stop, what should have been left? The answer is nothing. Nothing but light. A cosmos of pure radiation. No protons, no neutrons, no electrons, no atoms, no molecules, no chemistry, no solid ground, no liquid water, no gaseous atmosphere, no stars, no galaxies, no planets, no warmth, no life. Just an infinite, cold, expanding void filled with photons. A universe that is technically real, but effectively dead. Every equation physicists write, every simulation they run, every model of the early universe that obeys the known laws of physics gives the same result. The matter and the antimatter should have found each other and cancelled each other out with perfect precision. Every positive should have met its negative. Every credit should have met its debit. The books should have balanced to exactly zero. The universe should be empty, but you are here. You are sitting somewhere right now, in a room, in a house, on a planet, orbiting a star, inside a galaxy containing hundreds of billions of other stars. The air you are breathing is made of nitrogen and oxygen atoms. The water in your body is made of hydrogen and oxygen atoms. The carbon in your bones was forged in the cores of massive stars that exploded billions of years before the Earth formed. The observable universe contains something on the order of 10 to the power of 80 atoms of ordinary matter. That is, a 1 followed by 80 zeros, atoms. Real, solid, tangible atoms. This is not nothing. This is emphatically, overwhelmingly, undeniably something. The books did not balance. Something tipped the scales, and the amount by which they tipped is simultaneously laughably small and all-encompassing. For roughly every 1 billion pairs of matter and antimatter created in the Big Bang, there was one extra particle of matter, one lonely orphan with no antiparticle to annihilate against, one survivor out of every billion. When the great annihilation came, when the matter found the antimatter and the two destroyed each other in that final cataclysmic settling of accounts, the billion matched pairs were converted to light, gone, erased. But that single extra particle had no partner. It was left standing in the wreckage. And that orphan, that surplus, multiplied across the entire volume of the early universe, is everything you have ever seen, touched, or loved. Every mountain range, every ocean current, every cell in every living organism, all of it descended from that tiny, unexplained remainder. To fully appreciate how strange this situation is, you need to understand what antimatter actually is. And for that, we need to go back to 1928 and meet a young British physicist named Paul Adrian Maurice Dirac. Dirac was a man of terrifying intellect, an almost pathological quietness. His colleagues joked that a unit of conversation called the Dirac should be defined as 1 word per hour. But what Dirac lacked in social verbosity, he more than compensated for in mathematical brilliance. He was trying to solve a problem that sounds technical, but had earth-shattering consequences. He wanted to write an equation that described the behavior of the electron, the tiny negatively charged particle that orbits the nucleus of every atom, in a way that was consistent with both quantum mechanics and Einstein's special theory of relativity. The equation he produced, now called the Dirac equation, was elegant and powerful. It was also alarming, because it had 2 sets of solutions. One set described electrons perfectly. The energies were positive, the behaviors matched laboratory observations, everything was tidy and expected. But the second set of solutions described something that had never been observed. They described particles with the same mass as the electron, the same spin as the electron, the same magnitude of electric charge as the electron, but with the opposite sign. Where the electron carried a negative charge, these phantom particles carried a positive charge. Dirac was disturbed. He tried to explain the unwanted solutions away. He initially suggested that they might represent protons, the positively charged particles in the atomic nucleus. But this did not work. The proton is nearly 2,000 times heavier than the electron. The strange solutions describe something with the exact mass of the electron. No fudging could make the proton fit. So Dirac did something that requires either extraordinary confidence or extraordinary recklessness. He took the mathematics at face value. He declared that the phantom solutions were real. He predicted the existence of a particle that no human had ever seen, no experiment had ever detected, and no theory before his had ever imagined. A positively charged twin of the electron, an anti-electron. Today, we call it the positron. 4 years later, in 1932, an American physicist named Carl David Anderson was studying cosmic rays at the California Institute of Technology. Cosmic rays are high-energy particles from deep space that constantly bombard the Earth's atmosphere. Anderson was using a device called a cloud chamber, a sealed container filled with supersaturated vapor. When a charged particle passes through the vapor, it ionizes the gas molecules along its path, leaving a visible trail of tiny droplets, like a miniature contrail. By placing the cloud chamber inside a strong magnetic field, Anderson could determine the charge and mass of the particles from the curvature of their tracks. A negatively charged particle curves one way, a positively charged particle curves the other. Anderson saw something that made no sense, a track that curved the wrong way. It had the curvature radius of an electron, which meant it had the mass of an electron. But it curved in the direction that only a positive charge would curve. It was not a proton. It was too light. It was the positron. Dirac's impossible particle had been found in the wild. Antimatter was real. And it was not just the electron that had an antimatter twin. Over the following decades, as accelerator technology improved, and physicists gained the ability to create collisions of ever-increasing energy, a pattern emerged with the force of natural law. Every particle in nature has a corresponding antiparticle. The proton, discovered to have an antiparticle in 1955, when the antiproton was produced at the Bevatron accelerator at the Lawrence Berkeley National Laboratory in California by a team including Emilio Segre and Owen Chamberlain, who shared the Nobel Prize in 1959 for the discovery. The neutron, whose antiparticle, the antineutron, was confirmed in 1956 at the same facility. Every quark has an antiquark. Every lepton has an antilepton. The neutrino has the antineutrino. The pattern is universal and without exception. For every type of matter particle, there is an antimatter mirror image with the same mass, the same spin, but opposite electric charge and opposite internal quantum numbers. Antimatter is not exotic in the sense of being unusual in physics. It is predicted by the most fundamental equations. It is produced routinely in particle accelerators around the world. It even occurs naturally. Positrons are emitted by certain radioactive isotopes, and they are used every day in hospitals in a medical imaging technique called positron emission tomography, commonly known as a PET scan. Antimatter is exotic only in one sense. It is almost entirely absent from the universe we inhabit, and that absence is the deepest mystery in modern physics. How do we know the antimatter is gone? This is a fair question, and it deserves a careful answer. After all, if you were looking at a distant galaxy through a telescope, you could not tell whether it was made of matter or antimatter. An antimatter star would fuse antihydrogen into antihelium in exactly the same way that a matter star fuses hydrogen into helium. The light emitted by antimatter atoms would have the same wavelengths and colors as light from matter atoms. An antimatter planet orbiting an antimatter star would look identical to an ordinary planet orbiting an ordinary star. So how can astronomers be certain that the visible universe is made overwhelmingly of matter? The answer comes from the boundaries. If the universe contained large regions of matter and large regions of antimatter existing side by side, then at the borders between these regions, matter and antimatter would inevitably meet. Particles from one region would drift into the other, and when they met, they would annihilate. This annihilation would produce an unmistakable signal. Specifically, when an electron and a positron annihilate, they produce gamma-ray photons with a very specific energy, 511 kiloelectron volts. This energy corresponds exactly to the rest mass energy of an electron, and it is as distinctive as a fingerprint. If matter-antimatter boundaries existed between galaxy clusters or between large cosmic structures, we would see a glow of 511 kiloelectron volt gamma rays coming from those boundaries. We have looked for this glow. We have looked with orbiting gamma-ray observatories. We have surveyed the sky with instruments specifically designed to detect this signature, and we do not see it. There is no annihilation glow at the edges of galaxy clusters. There is no evidence of matter-antimatter interfaces anywhere in the observable universe out to the largest scales we can probe. But there is an even more powerful piece of evidence, and it comes from the oldest light in the cosmos. The cosmic microwave background radiation, or CMB, is the afterglow of the Big Bang itself. It was emitted roughly 380,000 years after the beginning, when the universe had cooled enough for the first atoms to form and for light to travel freely through space for the first time. That light has been traveling ever since, and it carries within it a detailed record of the conditions that prevailed in the early universe. By analyzing the tiny temperature fluctuations in the CMB, cosmologists can determine the ratio of ordinary matter to photons in the early universe with remarkable precision. The measurement tells a clear story. The universe started with a slight excess of matter over antimatter, and the amount of matter that survived annihilation is exactly consistent with the tiny surplus we have been discussing. The CMB does not show evidence of separated matter and antimatter domains. It does not show evidence of large-scale annihilation events after the initial epoch. It tells us that the asymmetry was baked in from the very beginning. The antimatter was created, it found its matter counterpart, they annihilated, and the tiny surviving surplus of matter went on to build the universe. The conclusion is inescapable. The observable universe is overwhelmingly, almost exclusively, made of matter. The antimatter is gone. It was destroyed in the great annihilation of the first seconds. And the matter that survived represents roughly 1/1000th of the original production. We are the residue. We are the ash left over from a fire that burned almost everything. Physicists have given this observation a name. They call it the baryon asymmetry of the universe. Baryons are particles made of 3 quarks. The proton is a baryon. The neutron is a baryon. They are the building blocks of atomic nuclei, and therefore the building blocks of every atom heavier than an electron. The baryon asymmetry is the measured fact that the universe contains far more baryons than antibaryons. The precise number has been determined from multiple independent observations, including the CMB, and the abundances of light elements produced during Big Bang nucleosynthesis. The period in the first few minutes when protons and neutrons fused to form hydrogen, helium, and traces of lithium. The ratio of the net baryon number to the number of photons in the cosmic microwave background is approximately 6.1 times 10 to the power of -10. In plain language, for every roughly 1.6 billion photons left over from the annihilation epoch, there is one baryon that survived. One proton, or one neutron, out of every billion pairs. That number might seem small enough to ignore. It is not. It is the most consequential number in the history of existence. If it was zero, there would be nothing. No chemistry, no biology, no geology, no stars, no planets, no carbon, no water, no DNA. The entire material complexity of the cosmos, from the web of galaxy filaments stretching across hundreds of millions of light years to the double helix of a single molecule inside one of your cells, depends on this number being non-zero. Everything hangs on it. And here is the statement that haunts every physicist who studies this problem. The standard model of particle physics, the most successful and most precisely tested theory in the history of science, cannot produce this number. It cannot generate the asymmetry. It cannot explain why the surplus exists. When you feed the standard model's equations into the conditions of the early universe, you get an asymmetry that is roughly 10 billion times too small. The theory sees the problem. It even has mechanisms that point in the right direction, but it falls short by a factor so vast that it is not a matter of fine-tuning or better calculations. It is a fundamental inadequacy. The standard model cannot explain why you exist. Let that settle for a moment. The standard model is not some fringe theory. It is the crown jewel of human intellectual achievement in the physical sciences. It describes 3 of the 4 fundamental forces of nature. It catalogues every known elementary particle. It predicted the existence of the Higgs boson decades before the particle was discovered at the Large Hadron Collider in 2012. It calculates the magnetic moment of the electron to a precision of roughly 1 part in a trillion, matching experiments with breathtaking accuracy. It is used every day in particle physics laboratories around the world. It works. It works spectacularly. And yet, it cannot answer the most basic question you could ask about the physical universe. Why is there anything made of atoms? This is the haunting. This is what keeps CERN scientists up at night. Not a ghost, not a conspiracy, not a secret locked in a vault. Something much worse than any of those things. It is the quiet, rigorous, mathematically airtight realization that the most powerful theory humans have ever constructed has a hole in it. And through that hole, everything we are came pouring in. Something beyond the standard model broke the symmetry between matter and antimatter. Something beyond our current understanding tipped the balance by that 1 part per billion. And whatever that something was, it has left no clear fingerprints that any experiment has yet managed to identify. Every collision engineered at the Large Hadron Collider, every antihydrogen atom trapped in a magnetic bottle at the antiproton decelerator, every precision measurement of a B meson decay at the LHCb detector is an attempt to force the universe to give up its secret, to reveal the mechanism, to show the scientists the hand that tipped the scales. But so far, the universe has remained silent. It sits there, made entirely of matter, functioning according to laws that say it should not exist, and it offers no explanation. The evidence of the crime is everywhere. You are the evidence. Every atom of hydrogen in every drop of water, every atom of calcium in every bone, every atom of iron in the hemoglobin molecules carrying oxygen through your bloodstream right now. All of it is stolen goods, plundered from a symmetry that should have been perfect, rescued from an annihilation that should have been total, and the detective work has only just begun. Because what comes next is the story of how physicists discovered that nature does in fact cheat, that the mirror between matter and antimatter is not perfectly flat, that there is a crack, But the crack, when they measured it, turned out to be far too small to explain the heist. And that discovery, that the crack exists but is insufficient, is what transformed the antimatter problem from a curiosity into a crisis. A crisis that CERN has spent decades and billions of dollars trying to resolve. A crisis that remains, to this day, unresolved. If the universe was supposed to annihilate itself and it didn't, then something intervened. Something reached into the first fraction of the first second of existence and tilted the playing field. Not by much. Not by a dramatic shove. By the smallest conceivable nudge. 1 extra particle per billion. But that nudge is the reason you have a body, instead of being a diffuse fog of ancient light. So the question that has consumed particle physics for over half a century is simple to state and devastatingly difficult to answer. What broke the symmetry? The first person to write down the recipe was a Soviet physicist named Andrei Dmitrievich Sakharov. Sakharov was a remarkable and contradictory figure. He was one of the principal architects of the Soviet thermonuclear bomb, the weapon that brought the Cold War to the brink of global annihilation. And then, driven by the moral weight of what he had helped create, he became one of the most prominent human rights activists in the Soviet Union, a dissident who was placed under internal exile by the government he had armed. He won the Nobel Peace Prize in 1975. But in between designing weapons capable of ending civilization and campaigning for the survival of civilization, Sakharov sat down in 1967 and thought about something even more fundamental. He thought about why civilization, or anything else made of atoms, existed in the first place. Sakharov identified 3 conditions, 3 requirements that the laws of physics must satisfy for a universe to evolve from a state of perfect matter-antimatter symmetry into the lopsided, matter-dominated cosmos we observe. These 3 conditions are now known as the Sakharov conditions, and they are the minimal ingredients for existence. If any one of them is missing, the asymmetry cannot be generated. The universe stays symmetric. The annihilation is total. Nothing survives. The first condition is that there must exist processes that violate the conservation of baryon number. Baryon number is a bookkeeping tool in particle physics. Every proton has a baryon number of +1. Every antiproton has a baryon number of -1. In ordinary interactions, the total baryon number before and after a reaction is always the same. If you start with 2 protons, you end with 2 baryons worth of stuff. If you start with 0 net baryon number, equal numbers of baryons and antibaryons, you end with 0. The books balance. Sakharov argued that somewhere in the early universe, there must have been reactions where this bookkeeping failed. Processes where the total number of baryons minus antibaryons could actually change. Without such processes, you could never go from 0 surplus to the 1 per billion surplus that built the cosmos. You could shuffle baryons around, convert them from one type to another, but you could never create more of them than their antiparticle counterparts. The second condition is the violation of 2 specific symmetries, called C and CP. This is the heart of the story, and it requires patience to understand, but the payoff is enormous because this is where the universe reveals its deepest and most unsettling bias. C symmetry, or charge conjugation symmetry, is the principle that says the laws of physics should look the same if you swap every particle with its antiparticle. Take any physical process. Now replace every electron with a positron, every proton with an antiproton, every quark with an antiquark. C symmetry says the resulting process should behave identically to the original. If it does, then any mechanism that creates a surplus of matter would be perfectly mirrored by an identical mechanism creating a surplus of antimatter. The net result would be 0. The symmetry would be unbreakable. P symmetry, or parity symmetry, is the principle that says the laws of physics should look the same in a mirror. Take any process and reflect it. Left becomes right, clockwise becomes counterclockwise. If parity holds, the mirror version of any interaction is physically indistinguishable from the original. Now here is where it gets critical. CP symmetry is the combination of both operations performed simultaneously. You swap all particles for antiparticles, and you reflect the process in a mirror. If CP symmetry holds, then even if C and P are individually violated, the combined operation restores the balance. The universe would still be unable to distinguish matter from antimatter in any way that could generate a lasting surplus. For the asymmetry to arise, CP must be broken. The combined mirror must be cracked. The third Sakharov condition is that these symmetry-violating processes must occur out of thermal equilibrium. Thermal equilibrium is a state of perfect balance, where every reaction going forward is matched by the reverse reaction going backward at the same rate. If the universe is in equilibrium, then for every process creating a baryon, there is a reverse process, destroying one at exactly the same rate. Any asymmetry generated in one direction is immediately undone. The early universe must have passed through a phase that was far from equilibrium, a period of violent transition, a sudden cooling, a dramatic shift in the state of the fields, where forward and backward reactions fell out of step. In that brief window of disequilibrium, the asymmetry could be generated and then frozen in, locked into the fabric of the cosmos, before the reverse processes could erase it. 3 conditions: baryon number violation, CP violation, departure from thermal equilibrium. That is the recipe. That is what it takes to build a universe from nothing. And for decades, physicists have been hunting for the kitchen where this recipe was followed. The first major breakthrough came from the second condition, the breaking of CP symmetry. And the story of how it was discovered is one of the most dramatic episodes in 20th century physics. By the early 1960s, physicists already knew that some symmetries of nature were not as sacred as they had believed. In 1956, 2 theoretical physicists named Sung-Dao Lee and Chen-Ning Yang made the bold suggestion that parity, the mirror symmetry, might be violated in the weak nuclear force, one of the 4 fundamental forces of nature responsible for processes like radioactive decay. Their idea was experimentally confirmed in 1957 by Chien-Shiung Wu in a famous experiment involving the beta decay of cobalt-60 nuclei. Wu showed that the electrons emitted in the decay had a preferred direction relative to the spin of the nucleus. A mirror reflection of the experiment would not look the same. Parity was violated. The universe was not perfectly symmetric under reflection. Li and Yang won the Nobel Prize that same year. Wu, despite having performed the decisive experiment, did not share in the prize, one of the most widely lamented oversights in Nobel history. But even after parity fell, most physicists still believed that CP symmetry was safe. They reasoned that nature might violate C and P separately, but the combination, swapping particles for antiparticles while simultaneously reflecting in a mirror, should still hold. This was comforting because CP symmetry is what prevents the universe from telling the difference between matter and antimatter at a fundamental level. If CP holds, then the laws of physics treat matter and antimatter as perfect, interchangeable reflections. The universe cannot prefer one over the other. There can be no asymmetry. The books must balance. Then came 1964. James Watson Cronin and Val Logsdon Fitch, 2 American physicists working at the Brookhaven National Laboratory on Long Island, New York, designed an experiment to study a peculiar particle called the neutral kaon. The neutral kaon, designated K0, is a meson, meaning it is composed of a quark and an antiquark bound together by the strong nuclear force. Specifically, the K0 is made of a down quark and a strange antiquark. Its antiparticle, the K0 bar, is made of a down antiquark and a strange quark. These 2 particles, the K0 and its antiparticle, have a strange and almost magical property. They can transform into each other spontaneously through the weak nuclear force. A K0 can become a K0 bar, and then become a K0 again, oscillating back and forth like a quantum pendulum. Because of this oscillation, Physicists found it more useful to describe the neutral kaon system not in terms of the particle and its antiparticle, but in terms of two different combinations that have definite lifetimes. These combinations are called K-short and K-long. K-short has a short lifetime and decays quickly, typically producing 2 pions when it breaks apart. K-long has a much longer lifetime and typically produces 3 pions when it decays. Now, the absolutely critical point. If CP symmetry were exact, if the combined mirror were perfect, then K-long would be forbidden from decaying into 2 pions. The mathematics of CP symmetry assigns the K-long a CP quantum number that is incompatible with the 2 pion final state. Only the 3 pion decay channel would be open to it. This is not a loose rule. This is a hard mathematical consequence of the symmetry. If CP is exact, K-long decays to 3 pions, period. Cronin and Fitch set up their experiment with meticulous care. They produced a beam of neutral kaons, allowed the K-short component to decay away, which happened quickly because of its short lifetime, and then studied the remaining beam, which should have consisted purely of K-long mesons. They placed their detectors downstream and watched the K-long particles decay. They expected to see only 3 pion decays. That is what CP symmetry demanded. They did not get what they expected. In a tiny fraction of events, roughly 2 out of every 1,000 decays, the K-long produced 2 pions. Not 3, 2. It was doing something that was mathematically forbidden if CP symmetry were exact. The violation was small. It was subtle. It could easily have been mistaken for an experimental error, a background contamination, a misalignment of the detectors. Cronin and Fitch spent months checking their results, eliminating possible sources of systematic error, convincing themselves that what they were seeing was real. It was real. The K-long was decaying in a way that it could only decay if CP symmetry were broken. The combined mirror between matter and antimatter was cracked. The physics community was stunned. CP violation had been considered nearly unthinkable. It implied that the laws of nature, at the deepest level accessible to experiment, treated matter and antimatter differently. Not by much, not by a dramatic amount, but by a definite, measurable, non-zero amount. For the first time, there was direct experimental proof that one of Sakharov's conditions was satisfied by the physical world. Nature possessed a built-in bias, a preference, a way of distinguishing the original from its reflection. Cronin and Fitch were awarded the Nobel Prize in Physics in 1980, and the excitement among physicists was immense. They believed they were closing in on the answer. If CP violation existed in nature, then perhaps it was CP violation that had tipped the scales in the early universe. Perhaps the kaon system, or something related to it, was the mechanism that generated the extra particle per billion. They had found the crack in the mirror. Now they just had to measure it precisely enough to show that it could account for the asymmetry. But before the measurements could be fully understood, the theory had to catch up with the experiment. And it did, in a remarkable paper published in 1973 by 2 Japanese physicists named Makoto Kobayashi and Toshihide Masukawa. At the time, only 3 quarks were known to exist: the up, the down, and the strange. Kobayashi and Masukawa asked a simple but profound question. Can the standard model, as it was understood in the early 70s, accommodate CP violation? The answer was no. With only 3 quarks, the mathematical structure of the weak nuclear force does not allow for CP violation. The equations are too constrained. There is no room for the kind of asymmetry that Cronin and Fitch had observed. But Kobayashi and Masukawa discovered that if there were at least 3 generations of quarks, meaning 6 quarks in total instead of 3, the mathematics changed dramatically. With 6 quarks, the matrix that describes how quarks transform into one another through the weak force, a matrix now called the CKM matrix, after Nicola Kabibo, Kobayashi, and Masukawa, acquires a single, irreducible, complex phase. This phase is a number that cannot be removed by any redefinition of the quark fields. And this phase is the sole source of CP violation in the quark sector of the Standard Model. This was a bold prediction. In 1973, the fourth quark, the charm, had only been theorized but not yet discovered. The fifth and sixth quarks were not even hypothesized by most physicists. Kobayashi and Maskawa were predicting the existence of at least two undiscovered quarks purely on the basis that CP violation required them. They were right. The charm quark was discovered in 1974. The bottom quark was discovered in 1977. The top quark, the heaviest of all, was discovered in 1995 at the Tevatron Collider at Fermilab. The full six-quark framework was confirmed, and the CKM matrix, with its single CP-violating phase, became the accepted explanation for the asymmetry observed in kaon decays and, later, in the decays of heavier mesons. Kobayashi and Maskawa were awarded the Nobel Prize in Physics in 2008, sharing the prize with Yoichiro Nambu, who was recognized for related work on spontaneous symmetry breaking. So by the end of the 20th century, the picture seemed to be coming together. CP violation existed. It was embedded in the Standard Model. It arose from a single complex phase in the CKM matrix. It had been confirmed experimentally in multiple particle systems. Sakharov's second condition was satisfied. The mirror between matter and antimatter was indeed cracked, and then the physicists did the calculation that broke their hearts. They took the measured amount of CP violation from the CKM matrix. They plugged it into the equations governing the early universe. They calculated how much matter-antimatter asymmetry this CP violation could produce under the conditions of the Big Bang, and the number they got was catastrophically wrong. The Standard Model's CP violation generates a baryon asymmetry that is approximately 10 orders of magnitude too small. 10 orders of magnitude. That is not a factor of 2. That is not a rounding error. That is a factor of 10 billion. The mechanism exists. The crack in the mirror is real. But it is so vanishingly faint, so microscopically narrow, that it cannot possibly account for the matter surplus that built the universe. It is as if you were trying to explain how a building was demolished, and you found a small crack in the foundation. The crack is real. You can measure it. You can photograph it. But it is a hairline fracture, and the building that fell was a skyscraper. The crack did not bring it down. Something else did. Something you have not found yet. This shortfall is not a matter of imprecise measurements or incomplete calculations. The CP violation in the CKM matrix has been measured with extraordinary precision over the past 3 decades. 2 purpose-built experiments, the Babar detector at the Stanford Linear Accelerator Center in California and the Bell detector at the KEK laboratory in Tsukuba, Japan. It spent the better part of 15 years making the definitive measurements of CP violation in the B meson system. B mesons are particles that contain a bottom quark, the heavy fifth quark, whose existence Kobayashi and Maskawa had predicted. The B meson system is a particularly rich laboratory for studying CP violation because the bottom quark couples to all 3 generations of quarks through the weak force, making it sensitive to the full structure of the CKM matrix. Babar and Bell were sometimes called the B factories because they produced B mesons by the hundreds of millions. They collided electrons with positrons at precisely the energy needed to create pairs of B mesons and anti-B mesons. They watched how these particles decayed. They measured the differences in decay rates between the B meson and its antimatter counterpart. They tracked the time evolution of the oscillations between particle and antiparticle. They analyzed dozens of different decay channels, and the results were definitive. CP violation in the B meson system was large, much larger than in the kaon system. In certain decay modes, the asymmetry between B meson and anti-B meson decay rates exceeded 20%. This was a dramatic confirmation of the Kobayashi-Maskawa mechanism. It was proof that the CKM matrix correctly described the pattern of CP violation in nature. Both experiments confirmed the standard model predictions with impressive accuracy, but that accuracy was a double-edged sword. Because what the experiments were confirming was that the standard model was correct, and the standard model's prediction for the baryon asymmetry was 10 billion times too small. After Babar and Bell had done their work, the baton passed to the LHCb experiment at CERN's Large Hadron Collider. LHCb, which stands for Large Hadron Collider Beauty, where beauty refers to the bottom quark, is one of the 4 major experiments stationed along the 27-kilometer ring of the LHC. It was designed from the ground up to study CP violation and the decays of particles containing bottom and charm quarks with the highest possible precision. LHCb has been running since 2010, accumulating vast quantities of data from proton-proton collisions at the highest energies ever achieved in a laboratory, and it has produced results that are simultaneously magnificent and maddening. In 2019, the LHCb collaboration announced a landmark discovery. They had observed CP violation in the decay of D0 mesons for the first time. The D0 is a particle containing a charm quark and an up antiquark. CP violation had previously been observed only in systems involving strange and bottom quarks. The observation in the charm sector was a significant extension of our experimental knowledge. It confirmed that CP violation operates across multiple quark families. It was a major experimental achievement. But the size of the effect was small, roughly consistent with the standard model's predictions. It added no new source of CP violation to the picture. It did not change the bottom line. And that bottom line is devastating. Every measurement of CP violation ever made, in kaons, in B mesons, in D mesons, is consistent with the standard model. The CKM matrix describes the data beautifully. There is no confirmed discrepancy between theory and experiment. No crack in the standard model's description of CP violation has been found. And this means that the only source of CP violation we have experimentally confirmed is the one that has already been shown to be hopelessly inadequate. The crack in the mirror is real, but it is not the crack that shattered the symmetry. Let us also check the other Sakharov conditions against the standard model, baryon number violation. The standard model does, in principle, contain a mechanism for this. It involves exotic quantum processes called sphalerons. Sphalerons are not particles in the ordinary sense. They are configurations of the electroweak fields, the combined electromagnetic and weak nuclear force fields that sit at the top of an energy barrier. At the low temperatures of the present universe, these configurations are astronomically unlikely to occur. The probability of a sphaleron process happening today is so small that it would not occur once in the entire lifetime of the universe. But at the extreme temperatures of the early universe, trillions of degrees, sphalerons would have been active. They could have converted baryons into leptons and vice versa, changing the total baryon number. This is promising. This means the first Sakharov condition is, in principle, satisfied by the standard model. But for sphalerons to be effective in generating a lasting asymmetry, they need to operate in the context of Sakharov's third condition, a departure from thermal equilibrium. And the most natural candidate for this departure is the electroweak phase transition. This is the moment in the early universe's history when the Higgs field, which had been in a high-energy symmetric state, settled into its current low-energy state, giving mass to the W and Z bosons and breaking the symmetry between electromagnetism and the weak force. If this transition were first order, meaning it happened suddenly and violently like water boiling, with bubbles of the new phase nucleating and expanding into the old phase, then the conditions for baryogenesis would be met. The bubble walls would be regions of extreme disequilibrium. Sphalerons would be active in front of the walls but suppressed behind them. CP violating interactions at the bubble walls could bias the production of matter over antimatter, and the bias would be swept into the bubble interior and frozen in as the wall passed. But the standard model fails here too. When physicists calculate the nature of the electroweak phase transition using the known mass of the Higgs boson, 125 giga-electron-volts as measured at the LHC, they find that the transition is not first order. It is a smooth crossover. There are no bubbles. There is no violent nucleation. The Higgs field rolls gently from one state to another, like warm butter softening on a counter, not like water suddenly boiling in a pot. The conditions for departure from thermal equilibrium do not arise. The third Sakharov condition is not met. So let us tally the score. Baryon number violation. The standard model has a mechanism, sphalerons, that works in principle but requires conditions that the standard model itself does not provide. CP violation. The standard model has it through the CKM matrix, but the amount is 10 billion times too small. Departure from thermal equilibrium. The standard model's electroweak phase transition is too gentle to provide it. The standard model fails on all three counts. Not in principle, but in practice. It has sketches of the right ingredients, but the quantities are absurdly insufficient. It is as if you had a recipe that called for a bonfire, a barrel of salt, and a cauldron of iron, and what you actually had was a birthday candle, a single grain of salt, and a thimble. The recipe is right. The execution is hopeless. This is why the baryon asymmetry is considered one of the strongest, most concrete, most undeniable pieces of evidence for physics beyond the standard model. Not a theoretical argument about elegance or beauty. Not a philosophical preference for simplicity. An observational fact. The universe is made of matter. The standard model cannot explain why. Therefore, the standard model is incomplete. Full stop. And this is why the scientists at CERN keep pushing. This is why LHCb is being upgraded for the high luminosity era of the Large Hadron Collider, which will deliver roughly 10 times more collision data than has been collected so far. They are not repeating the same measurements out of stubbornness. They are sharpening the blade. Every decimal place of precision they gain is a new opportunity to catch the standard model in a lie. A slightly unexpected branching ratio. A decay rate that deviates from prediction by 3 sigma, 4 sigma, 5 sigma. An angular distribution that tilts the wrong way. Any crack, any deviation, any whisper of disagreement between the standard model's prediction and the actual behavior of particles could be the thread that, when pulled, unravels the entire mystery. There have been tantalizing hints. Over the years, LHCb has reported several anomalies in the decays of B mesons, measurements that appeared to deviate from standard model predictions at the level of 2 to 3 standard deviations. These anomalies generated enormous excitement in the theoretical community. Papers were published by the hundreds proposing new particles, new forces, new symmetries that could explain the deviations. But as more data were collected and analyses were refined, some of the anomalies faded. Others persisted, but failed to reach the 5 sigma threshold that particle physicists demand before claiming a discovery. The situation remains fluid. The data are suggestive but not conclusive. The standard model is bending under the strain of precision measurement, but it has not yet broken. And this is perhaps the most psychologically grueling aspect of the antimatter problem. The physicists know the answer is out there. They know the standard model is incomplete. The existence of matter proves it. But the new physics responsible for the asymmetry is hiding. It is hiding behind a wall of precision. It is camouflaged within the enormous background of standard model processes. It might be operating at energy scales just beyond the reach of the LHC. It might be manifesting in particle sectors that current experiments are not optimized to probe. It might require a type of measurement that has not yet been invented. The situation is like searching for a specific needle in a haystack the size of a continent, knowing with certainty that the needle exists, because you are wearing the sweater it knitted, but having no idea what part of the continent it is buried in. The standard model is the haystack. The new physics is the needle. And every experiment is a probe, a metal detector, a systematic sweep of one more acre of hay. The physicists cannot give up. The sweater is too real. They are wearing it. They are made of it. Every atom in their bodies is proof that the needle exists. And so they keep searching. They refine their instruments. They expand their datasets. They check every anomaly, follow every lead, scrutinize every deviation. Because somewhere in the data, in the precise pattern of how quarks decay and mesons oscillate and particles transform, there must be a signal, a signature of the physics that broke the mirror. A clue left behind by whatever tipped the scales 13.8 billion years ago. The mirror between matter and antimatter is cracked. Cronin and Fitch proved that in 1964. Kobayashi and Maskawa explained the crack in 1973. Babar, Bell, and LHCb measured the crack with extraordinary precision over 3 decades. The crack is real, but it is too small. 1 billion times too small. 10 billion times too small. Whatever shattered the symmetry of the early universe used a hammer that we have not yet found. And every year that passes without finding it, every experiment that confirms the standard model yet again, adds another layer to the haunting. Because it means the answer is not where we expected it to be. It is not in the kaons, it is not in the B mesons, it is not in the charm sector. It is somewhere deeper, somewhere stranger. Somewhere that our current machines can barely reach, and our current theories can only guess at. The kitchen where the recipe was followed is locked, and we are standing outside, pressing our ears to the door, straining to hear the sound of the mechanism that built us. So far, all we hear is silence. And that silence, for a scientist, is the most unsettling sound in the world. If the collisions at the Large Hadron Collider represent the brute force approach to the antimatter mystery, then there is another strategy being pursued at CERN that operates at the opposite end of the spectrum. Instead of smashing particles together at 99.9999991% of the speed of light and sifting through the wreckage for traces of new physics, a different group of physicists has chosen to do something far more delicate, far more patient, far more technically absurd. They are building atoms of antimatter, one at a time, and they are holding them in place, suspended in nothingness, long enough to interrogate them. They are trapping ghosts. The facility where this happens is called the Antiproton Decelerator, or AD. It sits in a hall at CERN that few tourists ever visit. Compared to the cavernous underground caverns housing the Atlas and CMS detectors with their 7-story tall instruments and cathedral-like geometry, the AD hall is modest. It is a ground-level industrial space cluttered with cables, beam lines, cooling pipes, and clusters of equipment that look more like a plumber's nightmare than the frontier of human knowledge. But what happens inside this hall represents some of the most extraordinary experimental physics being conducted anywhere on the planet. Because inside this hall, scientists are doing something that would have been considered pure fantasy 50 years ago. They are manufacturing the rarest, most dangerous, most ephemeral substance in the known universe, and then they are holding it in a jar. The antiproton decelerator does exactly what its name suggests. It takes antiprotons and it slows them down. The antiprotons are created in the most violent way imaginable. A beam of high-energy protons from one of CERN's accelerators is fired into a dense metal target, typically iridium. The collision is so energetic that new particles are created from the impact energy, including proton-antiproton pairs. The antiprotons emerge from the target, traveling at close to the speed of light, mixed in with a chaotic spray of other particles. Magnets separate the antiprotons from the debris and steer them into the decelerator ring. Inside the ring, a carefully orchestrated sequence of electromagnetic braking maneuvers strips away the antiproton's energy, slowing them from relativistic speeds to something far more manageable. The process takes roughly a minute. The antiprotons circle the ring, losing energy with each pass through the cooling systems, until they are slow enough to be extracted and delivered to the experiments waiting downstream. This is already a remarkable feat. Antiprotons do not want to be slowed down. They do not want to be stored. They want to find a proton and annihilate. Every surface of the machine, every molecule of residual gas inside the vacuum chamber, every stray atom is a potential death sentence for an antiproton. The entire apparatus must operate at an extraordinarily high vacuum, billions of times lower pressure than the Earth's atmosphere, to minimize the chance of an antiproton bumping into ordinary matter and ceasing to exist. Even then, losses are constant. The antiproton decelerator produces roughly 30 million antiprotons per batch, delivered roughly every 2 minutes. That sounds like a lot. It is not. 30 million antiprotons have a combined mass of roughly 50 attograms. That is, 50 billionths of a billionth of a gram. If you collected every antiproton CERN has ever produced in the entire history of the antiproton decelerator program and put them together, the total mass would not be enough to warm a cup of coffee by a millionth of a degree. Antimatter is not just rare, it is expensive. Based on the cost of the infrastructure needed to produce it, antihydrogen is sometimes cited as the most expensive substance on Earth, with estimates running into the trillions of dollars per gram. Not that anyone has ever produced a gram, or a milligram, or even a microgram. The total amount of antimatter ever manufactured by human beings in the entire history of particle physics would not power a light bulb for a fraction of a second. But the physicists working at the AD are not trying to produce antimatter in bulk. They are trying to produce it in precision. They need individual antihydrogen atoms, and they need to hold them still long enough to study their properties with exquisite accuracy. This is the mission of the ALPHA experiment. ALPHA stands for Antihydrogen Laser Physics Apparatus. The name is functional, not glamorous, and the apparatus matches. It is a cylindrical device roughly 3 meters long, packed with superconducting magnets, electrodes, particle detectors, and laser systems. Its purpose is deceptively simple in concept and ferociously difficult in execution. It aims to create atoms of antihydrogen and compare their properties to those of ordinary hydrogen. Antihydrogen is the antimatter version of hydrogen, the simplest element in the universe. A hydrogen atom is one proton orbited by one electron. An antihydrogen atom is one antiproton orbited by one positron. If you could somehow look at an antihydrogen atom with antimatter eyes, it should appear identical to hydrogen, same size, same energy levels, same spectral lines, same response to light. At least, that is what the standard model predicts. And that prediction is precisely what ALPHA was built to test. Because if antihydrogen is not identical to hydrogen, if there is even the subtlest difference in how the two atoms absorb or emit light, it would signal a violation of one of the deepest theorems in all of physics, CPT symmetry. CPT symmetry is not the same as CP symmetry, which we already know is violated. CPT is the combination of 3 operations performed simultaneously. C swaps every particle for its antiparticle. P reflects the entire system in a mirror. T reverses the direction of time. The CPT theorem, proven mathematically in the 1950s, states that any quantum field theory that is consistent with both special relativity and quantum mechanics must be exactly invariant under this combined transformation. In plain language, if you take any physical process, replace all matter with antimatter, reflect it in a mirror, and run it backward in time, the result must be identical to the original process. No exceptions, no loopholes. This is not an experimental observation that might be overturned by better data. It is a mathematical consequence of the deepest assumptions of modern physics. If CPT is violated, then either special relativity is wrong, or quantum mechanics is wrong, or both. The entire framework of quantum field theory would have to be rebuilt from the foundations. One of the direct consequences of CPT symmetry is that a particle and its antiparticle must have exactly the same mass, exactly the same lifetime, and, for composite systems like atoms, exactly the same energy spectrum. If you shine a laser at a hydrogen atom and it absorbs light at a specific frequency, then an antihydrogen atom must absorb light at exactly the same frequency. Any deviation, no matter how small, would be a discovery of historic proportions. It would shatter the mathematical bedrock of particle physics. And, crucially for our story, it might point toward the new physics responsible for the baryon asymmetry. Because if matter and antimatter are not perfect CPT mirrors of each other, then the universe has a deeper way of distinguishing between them than anything the standard model currently describes. The asymmetry might not require exotic new particles or forces. It might be woven into the very fabric of how space-time and quantum mechanics fit together. So the stakes for alpha are as high as stakes can be, but the practical challenges are monstrous. To create antihydrogen, you need to combine antiprotons with positrons. The antiprotons come from the antiproton decelerator. The positrons come from a radioactive source, typically sodium-22, which emits positrons as it decays. Both ingredients must be cooled to extremely low temperatures, just a few degrees above absolute zero, to slow them down enough for them to combine. The antiprotons are captured in a device called a Penning trap, which confines charged particles using a combination of strong magnetic fields and electric fields. The positrons are accumulated in a separate trap. Then, with painstaking care, the two clouds of particles are brought together. The antiprotons pass through the positron cloud, and occasionally, one of them captures a positron and forms a neutral antihydrogen atom. And this is where the real nightmare begins. Because the instant the antihydrogen atom forms, it becomes neutral. It has no net electric charge. And that means the Penning trap, which relies on electric fields to confine charged particles, can no longer hold it. The antihydrogen atom drifts freely. If it touches the walls of the apparatus, which are made of ordinary matter, it annihilates instantly and is gone. To hold on to the antihydrogen, alpha uses a different kind of trap, a magnetic minimum trap. Antihydrogen, like hydrogen, has a tiny magnetic moment. It behaves like an extraordinarily feeble magnet. By creating a magnetic field configuration that is weaker in the center and stronger at the edges, the experimenters can create a shallow magnetic well. The antihydrogen atom, if it is cold enough and moving slowly enough, will be gently pushed toward the center of the well, bouncing back whenever it drifts toward the stronger field at the edges. It is held in place, not by walls, but by an invisible cage of magnetism. The trap is shallow, agonizingly shallow. The depth of the magnetic well corresponds to a temperature of roughly 0.5 Kelvin. This means that only antihydrogen atoms moving slower than a certain speed can be confined. Any atom that is even slightly too energetic will escape and annihilate on the walls. Out of the thousands of antihydrogen atoms produced in a typical mixing cycle, only a handful are cold enough to be caught. In 2010, the Alpha collaboration achieved a result that made international headlines. They trapped antihydrogen atoms for the first time in history. The number was modest, 38 atoms. The trapping time was brief, less than 0.2 of a second, but it was real. For the first time, human beings had held antimatter atoms in place long enough for the fact of their confinement to be verified by the annihilation signals produced when the trap was deliberately opened and the atoms hit the walls. Over the following years, the technique improved at a pace that bordered on astonishing. The number of trapped atoms increased from dozens to hundreds. The confinement time extended from fractions of a second to minutes, then to hours. By 2016, Alpha could routinely trap several hundred antihydrogen atoms per trial and hold them for more than 15 minutes at a stretch. This was long enough to start doing real spectroscopy, long enough to start asking the atoms questions and listening for their answers. In 2016 and 2017, the Alpha team performed one of the most important measurements in the history of antimatter physics. They used an ultraviolet laser to probe the internal energy structure of trapped antihydrogen atoms. Specifically, they targeted the 1s to 2s electronic transition. This is the transition in which the electron, or in this case the positron, jumps from the ground state of the atom to the first excited state. In ordinary hydrogen, this transition has been measured with almost ludicrous precision. The frequency is known to roughly 15 significant figures. It is one of the most precisely determined quantities in all of experimental physics. Measuring the same transition in antihydrogen and comparing it to the hydrogen value is a direct test of CPT symmetry. Any difference in the transition frequency between the two atoms would be a CPT violation. The alpha measurement was far less precise than the hydrogen measurement. This is unavoidable. You cannot hold antihydrogen atoms as long or as stably as you can hold hydrogen atoms, and the number of antiatoms available for study is minuscule compared to the vast clouds of ordinary hydrogen that spectroscopy labs routinely work with. But within the precision achieved, the result was unambiguous. The 1s to 2s transition frequency in antihydrogen was consistent with the corresponding frequency in hydrogen. No difference was detected. The mirror held. CPT symmetry was confirmed to the level of a few parts in 10 to the power of 12. This result was extended and refined in subsequent years. The Alpha 2 apparatus, an upgraded version of the original experiment, incorporating improved trapping magnets, better vacuum systems, and a more powerful laser, continued to sharpen the comparison. Each year brought higher precision. Each year brought the same answer. Antihydrogen and hydrogen are identical to within the experimental uncertainty. For physicists hoping that a spectroscopic crack, a tiny shift in a frequency, a subtle deviation in an energy level, might be the clue that solves the antimatter mystery, the results were deflating. The mirror between matter and antimatter, at least as probed by atomic spectroscopy, appeared flawless. But Alpha had another question to ask. Not about light, about gravity. For decades, a deceptively simple question had lingered at the margins of physics. Does antimatter fall down? When you say it aloud, it sounds absurd. Of course antimatter falls down. Gravity pulls everything down. Every apple, every rock, every satellite, every galaxy behaves as general relativity predicts. Gravity does not discriminate. But here is the subtlety that makes the question legitimate. General relativity has never been directly tested with antimatter. Not once. Every experimental test of gravitational physics, every observation of orbits and tides and gravitational lensing and gravitational waves has involved ordinary matter and ordinary energy. The equivalence principle, the foundational axiom of general relativity, which states that gravitational mass and inertial mass are identical, has been verified to extraordinary precision, but only for matter. For antimatter, the equivalence principle is an assumption, not a measurement. There have been theoretical proposals, admittedly speculative and outside the mainstream, suggesting that antimatter might respond to gravity differently than matter. Some models have explored the idea that antimatter could experience a repulsive gravitational force, effectively falling upward. This idea, sometimes called anti-gravity for antimatter, has been discussed in the context of alternative theories of gravity and even as a speculative explanation for the accelerating expansion of the universe driven by dark energy. Most physicists consider gravitational repulsion of antimatter to be extremely unlikely. It would violate the equivalence principle. It would create pathological consequences for energy conservation. It would be inconsistent with the behavior of virtual antiparticles, which contribute to the gravitational effects of quantum fields all the time without any sign of repulsion. But extremely unlikely is not the same as experimentally excluded. In physics, assumptions are not facts. Only measurements are facts. and no measurement of the gravitational acceleration of antimatter had ever been performed. This is what the Alpha G experiment was designed to change. Alpha G is a dedicated variant of the alpha apparatus, purpose-built to measure the gravitational free fall of antihydrogen. The key modification is the orientation. The trap is vertical. Antihydrogen atoms are confined in a magnetic bottle that is aligned with the gravitational field of the Earth. The bottom of the trap faces down. The top faces up. When the experimenters gradually reduce the strength of the magnetic confinement, the trap opens. The antihydrogen atoms, no longer held in place, begin to drift under the influence of gravity. If antimatter falls downward, like ordinary matter, the atoms should preferentially escape through the bottom of the trap. If antimatter somehow fell upward, the atoms would escape through the top. The annihilation detectors surrounding the trap register the precise location where each escaping atom hits the wall and is destroyed. By analyzing the spatial distribution of these annihilation events, the experimenters can determine whether the atoms fell down or up, and with what acceleration. In 2023, the AlphaG collaboration published their result in the journal Nature. The measurement was clear and unambiguous. Antimatter falls down. The antihydrogen atoms preferentially escaped through the bottom of the trap. The measured gravitational acceleration was consistent with the standard value of roughly 9.8 meters per second squared, with the direction firmly downward. The experiment ruled out gravitational repulsion of antimatter with high statistical confidence. General relativity's prediction was confirmed. The equivalence principle, at least at the level of precision achieved, holds for antimatter just as it holds for matter. This result was celebrated around the world, and rightly so. The experimental achievement alone was extraordinary. Producing antimatter atoms, cooling them to near absolute zero, trapping them in a magnetic bottle, orienting that bottle vertically, gently releasing the atoms, and measuring the direction of their fall, all while preventing them from touching a single atom of ordinary matter, is a technical feat that borders on the miraculous. And the result, while expected by most theorists, was scientifically important, precisely because it replaced an assumption with a measurement. Physics advances not by assuming things are true, but by proving them. And now the gravitational behavior of antimatter is no longer an assumption, it is a fact. But for those hoping that gravity might hold the key to the antimatter mystery, that some exotic gravitational asymmetry might explain why antimatter vanished from the universe, the result was another closed door, another wall tested and found solid, another avenue of investigation that led back to the same maddening conclusion. Antimatter behaves like matter. Gravity does not distinguish between them. While Alpha studies antihydrogen atoms, another experiment at the antiproton decelerator takes a different approach. The BASE experiment, which stands for Baryon-Antibaryon Symmetry Experiment, does not build atoms. It studies a single particle. Specifically, it studies the antiproton itself, in isolation, with a precision that verges on the obsessive. BASE confines individual antiprotons in a device called a penning trap. This is a cylindrical arrangement of electrodes and superconducting magnets that can hold a single charged particle suspended in vacuum essentially forever. The trap is cooled to cryogenic temperatures. The vacuum is so extreme that a single trapped antiproton can survive for years without encountering an atom of ordinary matter. BASE has maintained antiprotons in their trap for periods exceeding 400 days. A single subatomic ghost, suspended in emptiness, orbiting in tiny circles inside a magnetic field, month after month, while the physicists patiently measure its every property. What BASE measures is the charge-to-mass ratio and the magnetic moment of the antiproton. The charge-to-mass ratio is exactly what it sounds like. It is the ratio of the antiproton's electric charge to its mass. CPT symmetry demands that this ratio be exactly the same for the antiproton as for the proton, with opposite sign. BASE has measured this ratio and compared it to the proton value. The result: they are equal to a precision of better than 69 parts per trillion. That is roughly 11 decimal places of agreement. The antiproton and the proton are indistinguishable in their charge-to-mass ratio to a degree that is almost beyond comprehension. The magnetic moment measurement is even more technically demanding. The magnetic moment of a particle describes how strongly it interacts with an external magnetic field. For the proton and antiproton, this quantity is tiny, roughly 1,000th the magnetic moment of the electron. Measuring it requires detecting incredibly small shifts in the particle's oscillation frequency as the magnetic field is varied. Bass has measured the antiproton's magnetic moment and compared it to the proton's. The magnitudes agree to a precision of roughly 1.5 parts per billion, with opposite sign, exactly as CPT symmetry demands. Every measurement, every comparison, every test returns the same result. The antiproton is a perfect mirror image of the proton. The antihydrogen atom is a perfect mirror image of the hydrogen atom. Antimatter falls in the same direction as matter, with the same acceleration. The CPT mirror is flawless. Not a scratch, not a smudge, not the faintest hint of a distortion. And this is where the haunting reaches its most acute intensity. Because consider what the experiments are telling us. Every property of antimatter that we can measure matches the corresponding property of matter with extraordinary precision. The masses are the same. The charges are the same. The magnetic moments are the same. The atomic spectra are the same. The gravitational behavior is the same. Antimatter is not defective. It is not flawed. It does not carry some hidden weakness that caused it to lose the primordial competition with matter. It vanished from the universe despite being, to every measurement we can make, a perfect twin of the matter that survived. Imagine arriving at a crime scene. An entire population has vanished. Millions of individuals, gone without a trace. You examine the survivors. They are healthy. They are identical to the vanished population in every measurable way. Same DNA, same fingerprints, same blood type, same height, same weight. There is nothing about the survivors that distinguishes them from the victims, and yet one group exists and the other does not. You test every hypothesis. You scan for poisons that might have selectively targeted one group. Nothing. You check for environmental factors that might have favored one group. Nothing. You look for genetic differences, behavioral differences, structural differences. Nothing. The two populations are identical, and yet one of them is gone. That is the situation at CERN. The antimatter experiments have systematically eliminated every obvious explanation for the asymmetry. If the universe preferred matter because antimatter was heavier, the mass measurements would show it. They do not. If the universe preferred matter because antimatter interacted differently with gravity, the alpha-G measurement would show it. It does not. If the universe preferred matter because antimatter atoms had slightly different energy levels, the spectroscopy would show it. It does not. Every door that the experimenters push against is locked. Every wall they test is solid. But the physicists are not discouraged. They are sharpened. Because every null result, every confirmed symmetry, every door that refuses to open tells them something important. It tells them where the answer is not. And in a search space as vast as the landscape of possible new physics, knowing where not to look is almost as valuable as knowing where to look. Every closed door eliminates a class of theories. Every confirmed symmetry narrows the range of viable models. The prison of possibilities is shrinking. The ghost cannot hide in the rooms that have already been searched. And the precision of the searches continues to increase. Alpha is pushing toward higher and higher accuracy in its spectroscopic measurements. Each improvement brings the possibility of detecting a CPT violation at a level that previous measurements could not reach. Alpha Gear is working toward a more precise determination of the gravitational acceleration of antimatter. The current measurement confirms that antimatter falls down, but the precision on the exact value of the acceleration is still relatively coarse. Future measurements might be sensitive enough to detect subtle deviations from exact gravitational equivalence. BASE is developing new trapping techniques and measurement protocols to push the antiproton comparisons to even more extraordinary precision. And there are new experiments joining the search. GBAR, the gravitational behavior of antihydrogen at rest experiment, aims to measure the gravitational freefall of antihydrogen using a completely different technique. Instead of releasing atoms from a magnetic trap, GBAR plans to produce ultra-cold antihydrogen ions, strip the extra positron at the last moment to create neutral antihydrogen, and then watch the atoms fall freely under gravity in a pristine vacuum. This approach could ultimately achieve a precision on the gravitational acceleration that is orders of magnitude beyond what alpha G has achieved so far. The Aegis experiment, the antihydrogen experiment, gravity, interferometry, spectroscopy, is pursuing yet another approach, using a beam of antihydrogen atoms directed horizontally through a device called a moire deflectometer to measure the downward deflection caused by gravity. Each experiment probes the same fundamental question from a different angle, using different techniques, sensitive to different systematic errors. If there is a deviation hiding in the data, the overlapping coverage of these experiments maximizes the chance of catching it. Every one of these experiments is a question posed to the universe in a slightly different dialect, and the physicists know that nature sometimes reveals its secrets not in thunderclaps, but in whispers. The difference between matter and antimatter, if it exists at a level beyond what the standard model predicts, might be so exquisitely small that it has eluded every measurement made so far. But it might not be able to hide forever. The instruments are getting sharper. The trapping times are getting longer. The data sets are getting larger. The systematic errors are being beaten down. The net is tightening. But as of today, the ghost refuses to appear. The experiments have looked at antimatter from every angle they can devise. They have weighed it. They have measured its magnetism. They have shone lasers at it. They have dropped it. And every time, antimatter has stared back at them, a perfect reflection of matter, offering no clue, no anomaly, no deviation. The mirror is intact. The symmetry is preserved. And the antimatter that once filled the universe in equal measure to the matter that built your bones and your brain and every star in the sky is simply gone. Erased in the first seconds, leaving behind nothing but its absence. And it is that absence, that silence, that refusal to explain itself that haunts the scientists the most. They know the asymmetry happened. They know the mechanism exists. They know it left its mark on every atom in the cosmos. But the mechanism itself remains invisible. It hides behind a mirror so perfect that decades of the most precise measurements in experimental history have not found a single flaw. We have now walked the full perimeter of this mystery. We have examined the crime from every angle the experimenters can devise, the energy of the collider, the patience of the trap, the precision of the laser and the delicacy of the gravitational drop, and every approach has delivered the same result. Not a solution, not a clue, just a deeper confirmation that the question is real and the answer is absent. So now we must do the hardest thing. We must ask what this silence means. So now we must do the hardest thing. We must step back from the individual experiments and look at the full picture. We must ask what it means that after more than 6 decades of searching, the most powerful machines and the most brilliant minds in physics have failed to solve this problem. We must confront what the antimatter mystery tells us about the standard model itself, and we must look at where the search goes from here. Let us begin with a blunt assessment of the standard model's situation. The standard model of particle physics is, by any reasonable measure, the most successful scientific theory ever constructed by human beings. It describes 3 of the 4 known fundamental forces: the electromagnetic force, which governs the behavior of light and the interactions between charged particles; the weak nuclear force, which drives radioactive decay and certain nuclear reactions; and the strong nuclear force, which binds quarks together inside protons and neutrons and holds atomic nuclei together against the enormous electrostatic repulsion of their positively charged protons. It catalogues every known elementary particle into a coherent mathematical framework. 6 quarks, 6 leptons, the gauge bosons that carry the forces, and the Higgs boson, the particle associated with the field that gives mass to the W and Z bosons and to the fundamental fermions. The predictive power of this theory is staggering. Its predictions have been verified to a degree of precision unmatched by any other theory in any branch of science. No other framework has ever achieved such agreement between calculation and observation. The Standard Model predicted the existence of the W and Z bosons before they were discovered. It predicted the existence of the top quark before it was found. It predicted the existence of the Higgs boson decades before the particle was observed at the Large Hadron Collider in 2012. It is a monument to human intellect, and it cannot explain why you exist. This is not a minor footnote. This is not an obscure technical issue that only concerns a handful of specialists. This is a failure at the most fundamental level imaginable. The Standard Model describes the behavior of matter with extraordinary accuracy, but it cannot explain the presence of matter. It is like owning a perfect owner's manual for a car. Every wire, every bolt, every circuit described in flawless detail, while being completely unable to explain how the car got into your driveway. The manual is correct, every page is accurate, but the most important question, where did this thing come from, is answered with silence. We have already walked through the specific failures. Every ingredient Sakharov demanded is present in the Standard Model in name only. The quantities are wrong by factors so enormous that no refinement of the existing theory can close the gap. The Standard Model sees the shape of the puzzle. It recognizes the pieces, but it cannot assemble them into a picture that matches the universe we observe. The numbers are not slightly off, they are catastrophically off. And that catastrophic shortfall is not a problem at the periphery of the theory. It is a problem at the very center. But the baryon asymmetry is not the only crack in the Standard Model's foundation. It is the most philosophically striking, because it concerns the existence of matter itself, but it stands alongside several other failures that collectively paint a picture of a theory that is powerful but profoundly incomplete. Consider dark matter. Astronomical observations have established beyond reasonable doubt that roughly 27% of the energy content of the universe consists of a substance that does not emit light, does not absorb light, and does not interact with ordinary matter through any force except gravity. This dark matter shapes the rotation curves of galaxies, bends light through gravitational lensing, and leaves its imprint on the cosmic microwave background. Without dark matter, the large-scale structure of the universe, the web of galaxy clusters and filaments that stretches across billions of light years, cannot be explained. And yet the Standard Model contains no particle that could be dark matter. Every particle in its catalogue either interacts with light or decays too quickly to survive from the early universe to the present day. Dark matter demands new physics. It demands at least one new particle, and possibly an entire hidden sector of particles and forces that the Standard Model knows nothing about. Consider dark energy. Since 1998, observations of distant supernovae have shown that the expansion of the universe is not slowing down under the pull of gravity, as most physicists expected. It is accelerating. Something is pushing the universe apart, something that behaves like a uniform energy density permeating all of space. This dark energy constitutes roughly 68% of the total energy budget of the cosmos. The Standard Model offers no explanation for it. Quantum field theory, the mathematical framework underlying the Standard Model, does predict that empty space should have a non-zero energy density due to quantum fluctuations. But when you calculate this vacuum energy using the Standard Model's equations, you get a number that is approximately 120 orders of magnitude larger than the observed value of dark energy. That is not a discrepancy. That is the worst prediction in the history of science. Something is catastrophically wrong with our understanding of vacuum energy, and the Standard Model has no remedy. Consider neutrino masses. In the original formulation of the Standard Model, neutrinos were predicted to be massless. They were ethereal, ghostly particles that traveled at the speed of light and barely interacted with anything. But experiments conducted in the late 1990s and early 2000s, most notably at the Super Kamiokande detector in Japan and the Sudbury Neutrino Observatory in Canada, demonstrated conclusively that neutrinos oscillate between their three types: electron neutrino, muon neutrino, and tau neutrino. This oscillation is only possible if neutrinos have mass. The masses are tiny, at least 1,000,000 times smaller than the mass of the electron, but they are non-zero. The Standard Model cannot accommodate neutrino masses without modification. Something must be added. New fields, new particles, new interactions that the current theory does not contain. And consider gravity itself. The Standard Model describes 3 of the 4 fundamental forces. Gravity is conspicuously absent. General relativity, Einstein's theory of gravity, operates on completely different mathematical principles than quantum field theory. Attempts to combine the two, to write down a quantum theory of gravity, have been stymied for nearly a century. The two frameworks are individually successful, but mutually incompatible. At the energy scales where both would be important, such as the interior of black holes or the first instant of the Big Bang, the equations break down and produce nonsensical results. A complete theory of physics must eventually unify these two pillars. The Standard Model is silent on how to do this. The baryon asymmetry sits alongside these failures as one of the clearest signposts pointing toward new physics. But it has a unique character among them. Dark matter tells us there are particles we have not found. Dark energy tells us there is an energy we do not understand. Neutrino masses tell us there are interactions we have not identified. But the baryon asymmetry tells us something more personal. It tells us that the Standard Model cannot explain the existence of the very matter it describes. It is a failure not at the margins, but at the center. It is the theory's inability to account for its own subject matter, and that gives the antimatter problem a philosophical urgency that few other open questions in physics can match. So what might the answer look like? What kinds of new physics could generate the baryon asymmetry? Theorists have not been idle. Over the past 50 years, they have proposed a rich landscape of possible solutions, each elegant in its own way, each pointing in a different direction. One of the most studied proposals is electroweak baryogenesis. This idea attempts to make Sakharov's recipe work at the electroweak energy scale, the energy range probed by the Large Hadron Collider. The basic concept is to extend the Standard Model with additional particles, typically new scalar fields, related to the Higgs, that transform the electroweak phase transition from the gentle crossover we discussed into something far more dramatic. With the right additions, the transition becomes first order. Violent. Bubbles of the new phase nucleate in the hot plasma of the early universe, expand at a fraction of the speed of light, and their walls sweep through the surrounding material like shockwaves. At these bubble walls, the conditions are far from thermal equilibrium. The Higgs field is changing rapidly. The sphaleron processes that violate baryon number are active in the hot plasma outside the bubble, but suppressed inside. And if there are new sources of CP violation carried by the new particles, these CP violating interactions at the bubble wall can preferentially scatter quarks rather than antiquarks into the bubble interior. The sphalerons outside then process the remaining antibaryons, converting them into antileptons, while the excess baryons inside the bubble are frozen in, safe from further processing. The result is a net baryon number. Electroweak baryogenesis is attractive because it is potentially testable. The new particles it requires, additional Higgs bosons, new scalar fields, particles carrying new sources of CP violation, could be heavy enough to have escaped detection at the LHC so far, but light enough to be discovered at the high luminosity LHC or at future colliders. The first order phase transition it demands would produce gravitational waves, ripples in spacetime generated by the violent collisions of the expanding bubbles. These gravitational waves would have characteristic frequencies that might be detectable by the LISA space-based gravitational wave observatory, planned for launch in the mid-2030s. If electroweak baryogenesis is the answer, we might be able to hear the echo of the moment that created matter, ringing across the universe like the aftershock of a cosmic thunderclap. But the window for electroweak baryogenesis is narrowing. The Higgs boson discovered at the LHC has a mass of 125 gigaelectronvolts. This mass, combined with the measured properties of the Higgs, places tight constraints on extensions to the Higgs sector. Many of the simpler models of electroweak baryogenesis have already been excluded by LHC data. The surviving models require careful tuning and specific particle content that has not yet been observed. The idea is not dead, but it is under pressure. A second major candidate is leptogenesis. This idea takes a fundamentally different approach. Instead of generating the baryon asymmetry directly at the electroweak scale, leptogenesis generates an asymmetry in the lepton sector first, an excess of leptons over antileptons, and then converts that lepton asymmetry into a baryon asymmetry through Sphaleron processes. The mechanism was proposed in 1986 by Masataka Fukujita and Tsutomu Yanagida. It is built on the assumption that there exist very heavy right-handed neutrinos, particles that do not interact through any of the standard model forces and have masses far beyond the reach of any accelerator we can currently imagine. In the extremely hot early universe, these heavy neutrinos would have been produced in abundance. As the universe cooled, they would have decayed. And if their decays violate CP symmetry, if a heavy right-handed neutrino decays into leptons slightly more often than into antileptons, then a net lepton number is generated. The sphalerons, which were still active at these high temperatures, then partially convert this lepton asymmetry into a baryon asymmetry through processes that simultaneously change baryon and lepton number while conserving a specific combination of the two. Leptogenesis is beautiful because it connects the baryon asymmetry to the mystery of neutrino masses. The heavy right-handed neutrinos required for leptogenesis are the same particles that appear in the seesaw mechanism, one of the most popular theoretical explanations for why ordinary neutrinos are so much lighter than all other known fermions. In the seesaw picture, the smallness of ordinary neutrino masses is a direct consequence of the largeness of the right-handed neutrino masses. The heavier the right-handed neutrino, the lighter the ordinary neutrino. This links two of the standard model's failures together. Neutrinos have mass because of new particles that also explain why matter exists. Two mysteries, one solution. But leptogenesis has a profound drawback. The heavy right-handed neutrinos it requires are expected to have masses in the range of 10 to the power of 9 to 10 to the power of 15 gigaelectronvolts. The LHC operates at roughly 10 to the power of 4 gigaelectronvolts. The gap is at least 5 orders of magnitude and possibly 11. We cannot produce these particles. We cannot directly observe their decays. We cannot measure their CP violating properties. Leptogenesis may be the correct explanation for the baryon asymmetry, but it might also be permanently beyond our ability to test directly. There is, however, an indirect test. If leptogenesis is correct, and if the heavy right-handed neutrinos are Majorana particles, meaning they are their own antiparticles, then ordinary neutrinos should also be Majorana particles. And if neutrinos are Majorana, then a specific nuclear process called neutrinoless double beta decay should occur. In standard double beta decay, two neutrons inside an atomic nucleus simultaneously convert into two protons, emitting two electrons and two antineutrinos. This process has been observed. It is rare but real. In neutrinoless double beta decay, the two antineutrinos would annihilate each other inside the nucleus, and only the two electrons would be emitted. The total lepton number would change by 2. This has never been observed, but experiments around the world are searching for it with increasing sensitivity. Detectors filled with tons of enriched isotopes, buried deep underground to shield them from cosmic rays, are watching and waiting for the telltale signal. If neutrinoless double beta decay is found, It would prove that neutrinos are Majorana particles and would provide powerful circumstantial evidence for leptogenesis. Beyond electroweak baryogenesis and leptogenesis, there are other theoretical pathways. Affleck-Dine baryogenesis involves the dynamics of scalar fields carrying baryon number in the early universe, often in the context of supersymmetry. Spontaneous baryogenesis proposes that a time-varying scalar field creates an effective chemical potential that favors baryons over antibaryons during a specific epoch of cosmic evolution. Gravitational baryogenesis suggests that the interaction between space-time curvature and the baryon current during the expansion of the universe could generate an asymmetry. Some models invoke entirely new forces, new gauge symmetries, new sectors of particles that interact with ordinary matter only through gravity or through extremely feeble couplings. Each of these proposals satisfies the Sakharov conditions in its own way. Each is mathematically consistent. Each makes predictions, some testable and some not, and each remains unconfirmed. This is the landscape as it stands today. A single measured fact, the baryon asymmetry of the universe, and a garden of possible explanations, none of which has been singled out by experiment. The situation is simultaneously humbling and exhilarating. Humbling because after more than half a century of effort, we do not know the answer. Exhilarating because the answer, whatever it turns out to be, will represent a fundamental extension of our understanding of nature. It will reveal new particles, new forces, or new principles that we have never encountered before. It will open a new chapter in the story of the universe. And this is why the work at CERN continues. Not out of stubbornness, not out of institutional inertia, out of necessity. The universe has posed a question that demands an answer. And the physicists who work at the Large Hadron Collider, at the Antiproton Decelerator, at LHCb and Alpha and Base and G-bar are the ones holding the instruments capable of finding it. The high luminosity upgrade of the LHC, expected to operate through the mid-2030s, will deliver roughly 10 times more collision data than has been collected in the entire history of the machine. This flood of data will allow measurements of rare processes with unprecedented statistical power. Tiny deviations from standard model predictions that are currently hidden by statistical noise might become visible. New particles too rare to have been produced in detectable numbers so far might begin to emerge. The anomalies that have tantalized physicists in recent years, the slight disagreements between theory and observation in certain B meson decays, the whispered hints of lepton flavor universality violation, will either solidify into discoveries or fade into statistical noise. Either outcome will be informative. Beyond the LHC, there are proposals for entirely new facilities. The Future Circular Collider, a proposed next-generation machine at CERN with a circumference of roughly 100 kilometers, would reach collision energies up to 100 tera-electron volts, nearly an order of magnitude beyond the LHC. At these energies, the landscape of new physics would be laid open. Extended Higgs sectors, heavy neutral leptons, exotic scalar particles, entire classes of theories that are currently invisible would become accessible. The FCC could test electroweak baryogenesis directly. It could probe the Higgs field with enough precision to determine whether additional scalar particles exist. It could search for the heavy particles that many models of new CP violation predict. Meanwhile, experiments outside CERN contribute complementary pieces to the puzzle. The Deep Underground Neutrino experiment, known as DUNE, currently under construction with a FAR detector in South Dakota and a NEAR detector at Fermilab in Illinois, will study neutrino oscillations with sufficient precision to measure CP violation in the lepton sector for the first time. If the leptogenesis explanation is correct, there should be measurable CP violation in how neutrinos oscillate between their three flavors. DUNE will look for this asymmetry with a detector containing 40,000 tons of liquid argon, watching for the faint flashes of light produced when neutrinos interact with argon nuclei deep underground. The observation of leptonic CP violation would not prove leptogenesis directly, but it would establish that the lepton sector possesses the kind of asymmetry that leptogenesis requires. It would be the strongest indirect evidence yet. Gravitational wave observatories represent another frontier. If the electroweak phase transition in the early universe was first order, the collisions of the expanding bubbles would have generated gravitational waves with specific frequency characteristics. The LISA mission, a constellation of 3 spacecraft separated by 2.5 million kilometers, will be sensitive to gravitational waves in precisely the frequency range predicted by many first-order phase transition models. A detection of this primordial gravitational wave background would be direct evidence that the early universe experienced the kind of violent transition that baryogenesis requires. It would be hearing the sound of the moment that created matter, and the searches for neutrinoless double beta decay continue to scale up. Experiments like LEGEND, NXO, and CUPID are building detectors of increasing mass and sensitivity, pushing the limits on the half-life of this hypothetical process past 10 to the power of 27 years and beyond. If the signal is found, it will prove that lepton number is violated in nature, completing the experimental verification of the first Sakharov condition and providing a crucial piece of the leptogenesis puzzle. But there remains the sobering possibility that the answer lies beyond the reach of any experiment we can currently envision. The energy scales involved in some baryogenesis models, particularly leptogenesis with very heavy right-handed neutrinos, are so far beyond the LHC that no foreseeable accelerator could probe them directly. The mechanism that broke the symmetry might have operated at energies close to the grand unification scale, roughly 10 to the power of 16 giga-electron-volts, or even near the Planck scale, 10 to the power of 19 giga-electron-volts. These energies will never be achieved in a terrestrial laboratory. If the answer lives there, we will have to find it through indirect means, through the subtle fingerprints left behind in low-energy observables, through the patterns imprinted on the cosmic microwave background, through the properties of neutrinos and the spectrum of gravitational waves. It will require not just better machines, but better ideas, new theoretical frameworks, new mathematical insights, perhaps a completely new way of thinking about the relationship between matter, antimatter, and the structure of space-time. And perhaps that is the deepest lesson of the antimatter mystery. It teaches us humility. The Standard Model is a masterpiece. It is one of the greatest achievements of the human mind, but it is not finished. It is not the final word. It is a chapter, not the book. The universe is under no obligation to be fully describable by a theory that fits on a t-shirt. The equations that govern reality may be far stranger, far richer, far more layered than anything we have yet imagined. The antimatter problem is not just a puzzle to be solved, it is a signpost. It points toward territory we have not yet explored. It tells us that the map we carry is incomplete, and that the unmapped regions contain something essential, something without which the map itself makes no sense. Every atom of hydrogen in every star, every molecule of water in every ocean, every strand of DNA in every cell, every neuron firing in every brain that has ever pondered the nature of existence. All of it is a consequence of whatever happened in that first fraction of the first second. All of it is descended from that unexplained surplus. The one extra particle per billion. That particle is you. It is everything you have ever known, and the mechanism that created it remains one of the deepest unsolved problems in all of science. The scientists at CERN will continue. They will upgrade their machines. They will refine their measurements. They will trap more antihydrogen atoms and hold them longer and probe them more precisely. They will collide protons at higher energies and sift through the debris with sharper eyes. They will follow every anomaly, test every theory, close every loophole. And perhaps, in a year, or a decade, or a generation, they will find the answer. A new particle, a new interaction, a new symmetry that is broken in just the right way, a signal rising above the noise, like a voice emerging from static. And on that day, we will finally understand the mechanism that broke the mirror, the process that tipped the scales, the reason that matter won and antimatter lost, the reason there is something rather than nothing. But until that day, the haunting persists. It is there in the silence of the data. It is there in the perfect symmetry of every measurement that should be imperfect. It is there in the gap between the standard model's prediction and the universe's reality. It is there every time a physicist at CERN looks at the latest result from LHCb or alpha or base and sees, once again, that antimatter is a flawless reflection of matter, offering no clue as to why it disappeared from the cosmos. The universe is made of leftovers. We are the residue of an annihilation that should have been total. Every galaxy is an orphan. Every star is a survivor. Every atom in your body is a rounding error in the ledger of creation. And the entry that explains the error is missing from the book. The physicists know the page is torn out. They know the information existed. They know the ink is somewhere. But the book is 13.8 billion years old. And the page has not yet been found. So they keep turning pages. They keep looking. They keep measuring. Because the alternative, accepting that the most basic fact about the physical universe is beyond the reach of human understanding, is not something a scientist can do. The universe made us out of the surplus. It built our brains from the unexplained remainder. And those brains are now pointed squarely at the question of their own origin. There is a deep and almost absurd symmetry in that. The matter that should not exist is asking why it exists. The rounding error has become conscious and is demanding to see the books. And somewhere in the equations, somewhere in the data, somewhere in the still unbuilt machines and the still unthought theories, the answer is waiting, not hidden by malice. Not concealed by conspiracy, just hidden by the sheer depth and subtlety of the laws of nature. Laws that are stranger, richer, and more beautiful than anything the standard model has yet revealed. The haunting will end only when we find them, and we will not stop looking until we do.